Hello YouTube. Today I'm going to be covering the second question to the practice final exam for classical mechanics that I showed you guys the first problem for maybe a week ago. I can't remember, a week or 2 weeks ago. So the second problem is this. Two masses M1 and M2 interact by potential energy U equals 1/2 kr squared. So what's happening is you have like a mass M1, mass M2. You have an X and a Y axis, and they're moving in some direction, arbitrary, but they at the same time they're interacting with that potential energy U equals 1/2 kr squared. But at the same time, both particles are moving, and you don't know what direction they're going in yet. So let's use the Lagrangian to figure all this out. So the second part of the problem is the first part of the problem is find the Lagrangian in terms of center of mass and relative positions big R and little r. So as you may remember from the last video, there's a big X and a little x. This time there's a big R and a little r because there are two spatial dimensions, X and Y. So what big R is just saying is that if you have like two masses M1, M2, let's say M1 weighs more than M2 or has more mass than M2. Center of mass is going to be somewhere around here because mass is more concentrated towards the M1. And then what little r is basically saying, it's the relative position. So let's say you have two particles, M1 and M2. M1 is at 2, 2, and M2 is at 5, 5 in terms of Cartesian coordinates. Then their relative position is going to be 5 minus 2, comma 5 minus 2, or 3, 3. So that's their little r. So now let's find the Lagrangian before we move on to the second part. So the Lagrangian, we already know, is equal to T minus U, or kinetic energy minus potential energy. So do you remember that formula from last time that involved like the M's and the big X's and the R's? We have to reuse that. So we have 1/2 times big M, big R prime squared. This time we use R instead of X, plus 1/2 mu little r prime squared, where we know M is equal to M1 plus M2. Mu is equal to M1, M2 over M1 plus M2. I'll substitute it all in the end, don't worry. So now we can substitute in this later. We can make this substitution later. But just know that the reason why you can do this is because of the Pythagorean theorem. Because, say, I'm just going to draw a triangle here. If this is going to be your R prime or R, then this would have to be your big X prime or little x prime. This would have to be your Y, big Y prime or little y prime. And then the Pythagorean theorem basically just states that r prime is equal to square root of x prime squared plus y prime squared. And then the square root of that would also have to be true. So we can use this substitution later, but for now we can just solve for the Lagrangian in terms of r. So we know L is T minus U, so we have whatever we have in this T term, so this, minus 1/2 kr squared. And then we're done with the first part of the problem. Okay, I kind of crossed that out. Let me rewrite that. Okay, Now moving on to the second part of the problem, find the equations of motion for big X, Y, and big Y. That's gonna take a while, so let's get started. Let me write this on the top first. Okay, so we can get started by making this appropriate substitution. So now we'll have 1/2 m big X prime squared plus big Y prime squared plus 1/2 mu times little x prime squared plus little y prime squared minus 1/2 kr squared. Now let me get rid of this so it's not problematic anymore. Then we can use the Euler-Lagrange and set up 4 equations. So the Euler-Lagrange equations, we have to set up this d dt equals this, this, so let's solve for big X and big Y first of all, so we can describe the motion of the center of mass. So let's do this. So we can differentiate this whole thing in terms of big X prime. So we'll get that d dt of this of m times x big X prime is equal to the Lagrangian partial derivative with respect to big X, but big X is absent in this entire function, so we have 0. Therefore, m x double prime, because we know there's a d dt, since x prime is the same thing as saying d partial of x with respect to partial of t, taking the derivative of that with respect to time. So taking the derivative with respect to time only makes it the second derivative with respect to time. So this is equal to 0. Or in other words, big X double prime is equal to 0. And therefore, if you solve for that differential equation, you get AT plus B. So we know that the center of mass's motion is linear in the x direction. So you can expect it to travel in the x direction, the x component, either this way or this way at a constant speed and only going in one direction. Now, solving for y, we're going to get the exact same result as we got here, because if you differentiate this with respect to y prime, you're going to get my prime ddt of my prime equals 0. Then we're going to just end up with the same solution, so that we'll have y double prime equals 0. So y equals at, or okay, ct plus d, where we know a, b, c, and d are all arbitrary constants. So we know that y is also moving at a constant speed. The y component of the center of mass is going to be moving at a constant speed in one direction. So I'll just say that r is moving linearly. That's all I'm going to say. Now, we can solve for little x. Oh wait, why did I erase that? Okay, so what was that? 1/2 m big X prime squared plus Sorry, I'm really unhinged right now. I'm recording this at like 5 a.m. with no sleep. Okay, so now we can set up the Euler-Lagrange equations, but for, oh wait, it should be x squared plus y squared here. Forgot to make that a substitution. So now we can differentiate with respect to little x prime and little y prime using the Euler-Lagrange equations for little x and little y. So let's do that. Okay, so now let's differentiate with respect to little x prime. So we have d dt of mu times x prime, because you use the power rule on this function with respect to little x prime and you get that. Or mu x double prime, and that's equal to Lagrangian in terms of or Lagrangian partial with respect to little x. So that's negative kx. And then you'll get the same thing, you'll get the same equation of motion for y because nothing changes really, so you'll just have it in terms of y instead of x because the other variable goes to 0 when you take the partial. So let's get rid of that. We now have two equations of motion. Mu x double prime equals negative kx and mu y double prime equals negative ky. So it becomes clear that the motion is periodic, but let's just solve for the equations just to verify. So we know, and we only need to solve for one of them because the solutions are going to be the exact same since they're the exact same differential equation, but with different variables. So I'll just call them interchangeable for now. So mu x double prime plus kx equals 0. This looks awfully familiar to one of the concepts that I covered in one of my previous videos. So divide everything by mu first. So we now have x double prime plus k over mu x equals 0. Now we can find the characteristic equation for this second order differential equation since it's homogeneous linear. This is r squared plus k over mu equals 0. R equals square root k over mu I. So since it's just 0 plus or minus this, then we'll have a solution of x equals c1 cosine k over mu t plus c2 sine square root k over mu t. Same thing applies to y, so y also equals c1 cosine whatever I have written down. I don't have to repeat myself. Okay, so describing motion and the frequency. Well, the frequency is, kind of obvious. It's right here. So the frequency is going to be square root of k over mu. And we're pretty much done. So solution is r is moving linearly. So the center of mass is going to be moving at a constant velocity in the same direction. X and y are periodic with a frequency of square root of k over mu. Anyways, thank you for watching. I know I stumbled a lot and I kind of was a bit unhinged, but Forgive me, it's like 5 a.m. at the time of recording. Thank you for watching.